So today's class is a very different section of the organic chemistry chapter, which involves us trying to figure out what an organic compound, what properties might an organic compound have without the aid of chemical reactions. And this is a branch of chemistry called analytical chemistry. So this is your first introduction, or first foray into what we call analytical chemistry. And the idea is that can we analyze substances and organic compounds? You've done a bit of it in terms of chemical analysis. You did in O levels by using tests for cations and anions to discover what might some compounds have, what cations and what anions they have by using precipitation. Then in AS also you did the same. And in organic chemistry, we also use the reactions like with dichromate or manganate or 2,4-DNPH with visible observations to determine what chemical compounds they must have. But all of these processes require you to use up some of the reactant you want to find. So you have to have a good amount of it. But many times in life, we don't get to have too much of an amount to test it out. So we have to use other ways. There are multiple ways that we can analyze organic compounds without reacting them. One of them, which is what today's class is about, is using infrared spectroscopy. Spectroscopy, spectrometry, you've kind of already done that. You've already done mass spectrometry. And if you remember, mass spectrometry was the idea of using a mass spectrum to determine fragments and other and what do you call those? Isotopes of atoms. Okay, and in A levels, we're going to be using in second year and first year also. In first year, we'll be using something called infrared spectroscopy and using infrared radiation and the amount of radiation, infrared radiation that a chemical might absorb to tell us a bit about that molecule. And in second years, we'll also do something called NMR, NMR spectroscopy, which is nuclear magnetic resonance spectroscopy. That will be about radio wave absorption, and we'll talk about that later. The physics will not be too much of an issue for us. It's the chemistry that matters. And the idea and why this works out is that the basic idea that, and if you know enough physics, you know that infrared is part of the electromagnetic spectrum. So there's a certain wavelengths of electromagnetic radiation that are categorized as infrared. They have lower frequency than visible light, or larger wavelengths than visible light, for those who take physics, right? So the idea is that this is radiation of a sort. It's less than light radiation, but it's still radiation. It's a lower intensity than light. And the idea is that we can use infrared spectroscopy to identify functional groups in organic molecules. And the reason for that is that most compounds do absorb infrared radiation. But the infrared radiation has a pretty decent sized band of variation of the radiation. So by detecting what particular wavelength or frequency of radiation a molecule is absorbing, we can talk about its kind of bonds it has. And if you can figure out the kind of bond something has, we can figure out the functional group. For example, if you can figure out a molecule has, for example, a C double bond O bond, then you can tell that this compound might be an aldehyde, ketone, carboxylic acid, or ester. All right? And the reason for that is that most compounds absorb infrared radiation, and the wavelengths of the radiation they absorb correspond to certain frequencies. In this case, they happen to be infrared. Okay, so basically the idea is that we're going to be using infrared radiation absorption to determine the functional groups. And the reason for that is that there are certain polar groups and molecules that they vibrate with a certain frequency. Now, I'm giving you the basic physics intro just to explain to you where this idea comes from. Our job will not be to use this. Our job will be to just use the graph to determine functional groups. All right? And that's something I want to talk to you guys about after this. So, for example, this is just a background information. This is not required. This slide is also not required. But the idea is that their bonds that vibrate in particular ways, absorb radiation at a specific wavelength. And that happens to be the infrared wavelength spectrum. And so we can look at the infrared spectrum to identify functional groups. And even in the radiation they absorb, the certain frequency will match to a certain kind of bond. But we really need to worry about is an infrared spectrum. An infrared spectrum can be read to analyze the structure of an organic compound. Most importantly, we won't be able to tell basically the number of carbon atoms it has and all of that stuff, but we would be able to tell is if it's an acid or an alcohol or an ester or an aldehyde or a ketone, or does it have a carbon-carbon double bond. That's the kind of stuff you can be able to figure out from what you call it, these infrared graphs. All right? So this is what we're going to talk about. So the major use of infrared spectroscopy is determining the structure. Basically, the infrared spectrometer, the infrared radiation is generally in the range of 400 to 400 centimeters per second. Now this unit of centimeters per second is really the inverse of wavelength, which we call wave number. And for those who take physics, know that the the speed of light, which is a constant, is into the frequency into lambda, which is the wavelength. So basically, here 1 over wavelength is proportional to frequency, because this is constant. And you'll see the numbers wave numbers, which really are just proportional to frequencies. So we won't worry about the units as such, but it's called wave numbers. And we will have basically, let me use the graph to explain it, because that'll make more sense. So you'll see the word troughs on bands and wave number. So I'll explain both of them, showing you the graph. That makes the most sense. So here is what we call an infrared spectrum of propanone. You might remember propanone to be, and you should, not might, why am I being so polite with you guys? By this time you better remember what propanone is, huh? It's a 3-carbon ketone. So yeah. And basically what the idea is that when I pass a certain amount of infrared radiation varying from 0 to 4000 wave number, which is 1 over, I mean, there's a way to calculate this, but understand that the x-axis represents frequencies. So there were certain frequencies of electromagnetic radiation passed, and at times so basically whenever something is absorbed by the molecule, there would be this trough or a drop. You see, going up, and then this is a drop. And then there is a lot of drop right here. So starting from the left, drop, and then a lot more drops here. You'll realize that there's something called the fingerprint region. We'll talk about that later. We're starting from 0 all the way here to 4000 all the way here. But our focus will tend to be between 1500 to 4000. We'll talk about that a little later. So give me a few minutes before you can completely wrap your head around this. And if it's okay if you don't get everything right now, I'm just introducing the idea to you. So if there was no functional group in the compound, it'll just be like this, flat, around 95 or whatever percent. But when there are sharp drops like this and this, these are called troughs or bands. And these occur because of certain bonds in the molecule. So every organic molecule has a CH bond. So you'll always see kind of a trough here. But not every compound has a C double bond O. So for example, if you see this band, and now what we discovered was that when we did almost every ketone, there was always a drop in this region. And if we didn't have ketone, then the drop didn't exist. Now these drops are basically the radiation the molecule is absorbing. So basically, because the molecule had a C double bond O, it absorbed certain radiation corresponding to this wave number. If the propanone did not have the C double bond O, then this would have just continued. So it would have not absorbed it, it would have transmitted it. Like transmission is basically what you absorb and then you transmit back out. But because it was not transmitted, it was completely absorbed by the molecule right here. So the idea being that when you take propanone, let's say butanone would have a very similar graph, because butanone would be what? Butanone would be CH3, CH2, CO, CH3. Has a C double bond O and CH bonds. Propanal, which is CH3, CH2, CHO, would also be similar like this, because propanal also has a C double bond O bond and CH bond. So the only two bonds in these three molecules, CH and C double bond O. So all of these three, by the way, will have similar drop near 3000 and and a much larger, or whatever, we don't care about the depth of the drop right now as much. Imagine that the depth didn't matter to us. So there was a drop in around 3000 wave number and a drop near 1700 wave number. The 3000 wave number always kind of corresponds to CH. And this kind of information will be given to you, that if a drop occurs at 3000, then you can deduce that it must be a CH bond. If a drop occurs near 1700, then it must be a C double bond O. That's all we can tell. We can only tell the kind of bonds that exist in a molecule. We cannot tell anything more. We cannot tell the number of carbon atoms. We cannot tell the mass of the molecule. None of that. So yeah? Then we are going to worry about this. Now, this region, so basically, now the reason why I give you these three molecules on the board, on this slide right here, CHO, which is like aldehyde, 3 carbon aldehyde, 3 carbon ketone, and 4 carbon ketone. All three have somewhat the same bonds. The functional groups are not identical, by the way. Aldehydes have other reactions and ketones have other reactions. And the two ketones are not the same because they have different number of carbon atoms. But this region of 1500 to 4000 will be almost identical to all three. There will be slight variation, but you can't even tell those variations because it'll be in the margin of error. What will be different is that this lesser energy radiation, which we have so far ignored, which is labeled as the fingerprint region. Now this region will be unique to every individual molecule. So the molecule propanone might look like this, but propanal will be very different than this. So what I was saying was that this region would be the same through all three compounds, but the fingerprint region will be very different for this fellow, which is propanal, propanone and butanone. All three will have a different fingerprint region, this drop. Obviously, every propanone, meaning today and tomorrow and ever, will always have the same. But propanone and butanone will not have the same fingerprint region, but they will have the same this region. Now the funny thing is, this region is predictable because they will be determined by the type of functional group bonds they have. And our concern in this year's exam will be, or actually any exam will be this region. But in the real world, we can have data, because remember, fingerprinting, the idea of fingerprinting stems from actual human fingerprinting, but it has been extrapolated. What it means is that fingerprinting is the idea that you take a sample of something unknown and match it to a known database of samples, and whatever matches must be your guy. DNA fingerprinting happens that way. Infrared fingerprinting. Tomorrow, for example, so you are maybe a chemical analysis company. You will have millions of molecules ke fingerprint region data. So tomorrow, if I give you XYZ molecule, let's say I give you propanone, you might remember, and you do not know it was propanone. So you'll get this, and you might say, well, the compound is an aldehyde or a ketone. That's all I can tell you by looking at this region. But in the real world, what will also happen is that your computer will be able to match this fingerprint region for the unknown molecule to the whole database of fingerprint regions they have. And from that, the computer will definitely tell you that, oh, you added propanone. But we cannot use it because we don't have the database of fingerprints. So the Cambridge is concerned with the fact that can you analyze data and, like a detective, you figure out what at least functional groups you have. So for all intents and purposes, you guys are going to ignore the region below 1500. You're only going to be focused on the region above 1500 to 4000. That is the region where the functional groups are. And that's something that you got to remember. All right. Now, let's move on. Let me explain fingerprint. You need to understand the philosophical idea of a fingerprint before we can explain fingerprint region. A fingerprint is that tomorrow that you match a sample that you don't know kis cheez ka sample hai, and you have uska fingerprint region, and you can match that to the database of all molecules, and only one unique molecule will have the same fingerprint as this. Just like if we could find all the fingerprints of everybody in the world and then we match your fingerprint to the whole list, your fingerprint will only match one copy in that whole list, which is your own fingerprint. But this region will not just match only one. Almost all aldehydes and ketones will have this trough almost exactly here, and you cannot tell because they'll all be the same. So fingerprint is the region that is unique to each molecule. All right. Let me repeat what I was saying. So the fingerprint region will be able to help us identify each unknown sample's graph to exactly what the molecule is. But uske liye we'll have to use a computer. It will not need it will not need your and my deduction. What we are going to be concerned with is only and only the region after the fingerprint. Because below the fingerprint, there's no science involved, right? Because the only one molecule will have this exact same graph will be propanone. So there's nothing much to do there except for use a computer to match this molecule's fingerprint region to unknown, because let's say you did not know this was propanone. This was an unknown ka graph. But you already have propanone ka graph. And you will realize that propanone's graph and this molecule's graph on this region matched. Ditto. But it is not necessarily the case with this region. This region will match for propanone, butanone, hexanone, pentanone, methylpentanone, butanone, whatever. No methylbutanone, but you get what I'm saying. Ketones and aldehydes will have similar such regions. Okay? So, one of the questions was margin of error. No, there's no margin of error. There is nothing more than functional groups you can determine from this side. There is no margin of error there in determining functional groups, but there is no way to tell the molecule from this side. And the fingerprint region will tell us exactly what the molecule is, but you will not be asked to determine the molecule from the fingerprint region. This region is literally for you to ignore. Look, I will not even talk about it after this. You will not be asked to look at it, discuss it, use it, nothing, nada. Okay? Now let's look at a couple of more examples and then maybe it'll make more sense after this. Okay? And somebody asked, how will I know if it's aldehyde or ketone? By using the graph, you cannot know. Nope. The other ways, not through the graph. So the graph is not a foolproof method, it's limited. And they want to play with that limitation and see what you guys can understand from it. So this is what I was saying was that we could identify the CH bonds and the CO bonds, but the fingerprint region characterizes the whole molecule as a whole. And we can compare that with database of infrareds and use to identify the molecule. But that will not be your job. Your job will be to use the infrared spectrum after or above the 1500 region, and then for that region, the butanone and propanone will have similar bands or similar troughs because they're the same functional groups. Okay. Now, you will be given data, obviously in the data booklet. So, let me explain to you just a rough idea of where you find some bonds. So, below 1500 is something we will never look at, so that we ignore it. Very close to 1500. Between 1500 and 1700, you'll find the double bonds. Basically, so if you find troughs between this is a good way to roughly summarize it. And obviously, we'll look at more exact values later. But right after the fingerprint region, right above 1500, you will be able to see 1500 to 1900, you'll be able to see the two double bonds. 1900 to 2500, you will be able to, if they have a band there, it'll represent either the carbon-carbon triple bond or the carbon-nitrogen triple bond, which is found in nitriles. And the single bonds are all above 2500. You got the carbon or hydrogen single bond, oxygen hydrogen single bond, which is found in alcohols and carboxylic acids. And NH is basically found in a lot of organic molecules that you really study in second year. Nitrogen's organic chemistry you study in A2. Okay, there are other bonds also. There is the carbon halogen bond, which tends to be found somewhere in the fingerprint region. So fingerprint ke alawa us region may be some of the molecules will show bands there also. And so we will be given these numbers. So don't worry about it. But some of the more important ones, I'm going to zoom in. First of all, look at this table. You will realize that that you can look inside the fingerprint region for something also. Like if you remember, the CO bond is present in esters, in acids, and in alcohols. Because in alcohols, it would be basically ROH. The R to O is a CO single bond. Acid is RCO OH. So this CO is this bond. And in esters is RCO OR dash. So CO bond is occurring in alcohols, esters, carboxylic acids, and something called ether that we don't study really in A levels. And it will not be in the region above 1500. It will be found within the fingerprint region also. Okay. So there will be other, so the idea is that you will have to look at some of these to nullify. So that, for example, what the idea that we are going to be using is that we'll check, are there troughs or bands in these regions? And if there are bands, they will highlight what bond exists, and if there are no bands, they will tell us what bonds don't exist. Some of these, like the first two, are going to be within the fingerprint region, meaning that in the fingerprint region, what you need to understand is this. Listen, guys. That the reason why that is called a fingerprint is you're going to find a lot of troughs there. And you'll have to ignore most of them, because we can't tell the functional groups from that. In the non-fingerprint region, the only troughs that you will see are for specific bonds you're looking for. But in the fingerprint region, you will have one or two that will be maybe because of the bonds, like CO and CCl. And the rest will be fingerprint that we'll have to ignore. And there are other certain bonds that are very popular. Like, you'll realize that this is very, 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 very good. The CO, this is the most popular, because CO is present in aldehydes, ketones, acids, and esters. Whenever you have a C double bond O, and in the very, very specific 1700 to 1750 range, you're going to have a trough or a band. And this fellow is very popular. Most, when they give you questions with an infrared, they tend to have an oxygen molecule, and generally you will see it either way: aldehyde, ketone, acids, and ester. So if they say, hey guys, I have a molecule that has one oxygen, but when they show you the IR graph, there was no trough in this region, then you can rule out the molecule being an aldehyde, ketone, acid, or ester. And if you can rule that out, you're left with only alcohol then, right? That also helps. You can also, when you have OH, there are two kinds of OHs. You see, there's an OH and an OH. So OH in an acid is 1000 units wide, but OH of an alcohol is smaller. And now when we look at some of these graphs, you'll start learning them through the graphs. The values will not be as important as looking at the graphs. So that's what I'm going to look at. Okay, I'm actually going to skip this and let's look at the graph for a second. So let's go to slide number 14. I'll do 2-3 graphs and then I'll ask you if you understand this or no. Okay, so our job is to use the data book, the table that we've given. We know that there is a fingerprint region where I have to ignore most of the troughs. Above the fingerprint region, this molecule had actually one trough at near 1700 and one that starts from about 2400 all the way to 3400. You see that? We call this a very broad peak. And the reason why it's a very broad peak is because this, if something you find this wide or broad and then it goes deep and comes back up, this is extremely characteristic of carboxylic acids. So whenever you find very fat, broad, like wide valley coming back up, for you guys it's like a mountainous valley coming back up, but wide valley, not a very narrow but a wide valley. This will only be carboxylic acids. So anytime you see this, and I'll show you some more examples. In fact, let's look at a couple of examples. Like, check this out. This is ethanoic acid, and this is a graph. And look at the valley going deep and coming back up from about 24,300 to 3,500. 1,000 units wide, D goes up. This is because of the the OH of COOH. Let me show you something else similar to here. Look at these two fellows. This has a very wide valley, wide. So by looking at this graph, I can right away say, hey, T must be a carboxylic acid. Let me show you some more examples. Since in this case, none of them have that wide trough. This is two peaks, it's not one. So we know this is not an acid, this is not an acid. And looking at 27, you can figure out that this looks like to be the acid, very deep. This is also wide, but it seems to be two separate ones. And we look at more detail a little later. But you guys start getting the idea. Let me show you one more example if I can find an acid here. Yeah, right there. So look at this example. Of all the three graphs, just from what we have studied, you'll realize that, hey, this fellow right here has the widest, broadest peak. So this looks like it must be an acid. All right? So that's the first thing I want you to start realizing, that this how easy it is to identify at least one functional group. Which functional group? Carboxylic acids. That's what I want to start off with first. And I'll continue everything else, but this part right here. Remember, a carboxylic acid has unique functional groups, bonds. So you are looking for the CH bond, which exists in every molecule. So that will be in, that's the one that's right here. You're also looking for a CO bond and an OH bond. This is the OH bond. You're also looking for a C double bond O. And the C double bond O is always going to be found between this exact specific region. And that C double bond O could be an acid, ester, aldehyde, ketone. So this had the C double bond O, but it had this broad peak also. Okay, if it didn't have the broad peak, then it would not have been an acid. It would have been an aldehyde, a ketone, or an ester. And then you look for other things. Now, there is a peak at this area is not very usable, by the way, because the peaks could be because of the bond or something else. That's the problem. So whatever peak that exists here could have been because of CO or other things. But the fingerprint region can, if there was no peak in the region that was CO, then we could say that this molecule has no CO bond. But let's go to the fingerprint region area later about what to see from there. Let's focus on only the area above 1500. And here, if it's a big carboxylic acid, is going to have a C double bond O and an OH. All right? And let me do a few more molecules before let it sink in with you. Remember, butanoic acid, we were looking for the region between 1500 to 4000. And we saw the CO, which was near 1700, and the very broad OH, which told me it's an acid. The CO single bond is in the fingerprint region, and it's never really easy to see there. Now, let's look at another molecule. In this case, this is propan 1-al. Therefore, it's an alcohol. Now, if I make the molecule, it is CH3, CH2, CH2, OH. Now, this follow has an OH bond, CH bonds, and C single bond O. So really, this molecule has a lot of CH bonds, one CO bond, and one OH bond. Only 3 different bonds that it has. And when you look at the data booklet that we have for these things, you'll realize that this fellow will always be found in the fingerprint region. So even though it's marked here, I couldn't care less about this fellow. We'll talk about this guy later. CH is found in every molecule, organic chemistry molecule. So it doesn't really matter. It's found near 3000. But because it has an OH, it has a peak near about 3500. You see that right here? Now, you will find this values in the data booklet. And what would the data booklet look like? Well, when you look at the graph, there was a value at 3500, and then you look at this graph and you look at the data. What is for 3500? Either it's an amine or alcohols, OH, or acids. Acids ke liye it has to have a broad peak. And then the molecule either is an alcohol or an amine, which is an NH group. But they will be telling you the molecular formula or even the elements involved. So if I told you that the compound only has carbon, oxygen, and hydrogen, and you had a value near 3500, the only possibility was an OH group. Which means that by looking at the graph, let me go there, where is it? I can confirm that it is an alcohol group. That's how it is. Because look at all the molecule bonds here. All the CHs, CO, and OH. These are all, so there will be a CH spectrum, an OH spectrum, and a CO spectrum. Now, ethanol will have something very similar. Because if this is propanol, ethanol has the same number of bonds. So what you start realizing is that, hey, this is near 3500. Remember, 3500 is basically your. So I am going to mark this fellow. I'm going to scroll up thoda sa. And so this band is because of the OH. This band is because of, and I've been doing this so I know that, but the highest value is always for the OH. And these are 2 different bands. It's not one peak, these are 2 different peaks. And you notice something here, that whenever I see oxygen, I am going to try and search for something in the 1700s. And this is non-existent because it has to be deep. So you realize that 1700 pay, it doesn't have a peak. So what can I say? It definitely has. It does. What it doesn't have is, it doesn't have a C double bond O. So therefore, if I did not know this is ethanol, I knew this molecule will have an OH because a dip at 3500 tells me it's an OH. But it does not have a C double bond O, meaning it is neither an aldehyde, nor a ketone, nor an acid, nor an ester. This helps there. And because there's no broad peak, it's not even an acid anyways from here. So it either must be an alcohol then, most likely. All right. Now let's look at some other examples. Yeah. So this molecule that I've placed in front of you is called ethyl ethanoate. And the graph is for ethyl ethanoate. And what is ethyl ethanoate? Ethyl ethanoate is an ester. So I'm going to make the molecule on the top. And what you realize is certain distinct bonds. It's going to have CH bonds. It's definitely have a C double bond O. It has a C single bond O. C single bond O here also and here. The quantity of bonds will not matter to us. So it has three types of bonds. It has CH all across here. It has C single bonds O's and it has C double bond O's. And from what I know about these bonds, I know that this occurs in the fingerprint region, so I don't care about that one. I care about the CH and the C double bond O. And the C double bond O is literally the first thing I look at. This is my fingerprint region, so I can just discount that. I've ignored that, all of that. Now, just after the fingerprint region, at about 1700, I see a dip. And because I see a dip, let's say I did not know the structure of the molecule. Because I see this dip, I can tell you that the molecule has a C double bond O. Alright? But we do not know if it's an aldehyde, ketone, or acid, or ester. But by looking at this side, there is no broad peak. Therefore, it is not an acid. Why? Because it doesn't have a broad peak. It doesn't even have an OH peak. It has just a peak at 3000. A peak at 3000 that is not broad tends to be because of the CH bond. So this peak is because of your CH bond. So if I had not known the formula of the compound, I could say that this molecule is either an aldehyde, ketone, or carboxylic, ester. Okay? But one thing is that we also got to realize that इसमें C double bond O भी है. Now the C double bond O comes in near where? 1000 or so. 1300. Now, if you look at 1000, there are multiple peaks here, and we do not know if it's because of the fingerprint region or this guy. But because they exist, the possibility of it being an ester still exists. If there was no peak at the CO band range, then we could have definitely said कि भाई this is not an ester. But because there is, we cannot confirm nor deny if it's an ester, aldehyde, or ketone just by this data, and that's okay. That's what we want to line up to. We want some deductions, not too much. Or we cannot get too much from this. We already discussed this. So basically, how do I know it's ethanoic acid? Well, there are two distinct features about this making an ethanoic acid. Because again, so I'm going to highlight the area that I'm not going to look at first, which is your fingerprint region. So all of this I am not looking at. So outside the fingerprint region, what do I have? I have a dip at 1700 and a broad dip at that starts from 25 to 35. So the examiner will need to know, can you determine what this is for? Well, this is because of the C double bond O. And this broad peak is because of not just any OH, but the OH found in Q. So what can I say from this graph? That this molecule is a carboxylic acid. And just being able to compare three graphs would help you understand this. All three are compounds, and this one on the right was ethanoic acid because it has a CO group and an OH from an acid group. Ethyl ethanoate has a C double bond O group, which is literally missing in ethanol. You see that? At 1700, nothing was in ethanol. So if I had to figure, I would say that this does not have a C double bond O, so it's neither an aldehyde, ketone, acid, or ester. This is definitely an acid. And this fellow could be an aldehyde, ketone, carbox, or ester. All right? That's all I could determine. Okay, so let's try a question out. The kind of things that they'll expect you to be able to do. So this skill check says that compounds T and W have the formula C3H6O2. So now we know there are two oxygens, right? And a C3H6O2. So C3H6O2, one option is CH3, CH2, COOH. If you look at this, there is 3 carbons, 2 oxygens, because 2 may, you tend to think about, could be an alcohol, could be an acid, could be an ester, but either if it's an alcohol, there must be 2 OHs, or ketone, then 2 ketones, or 1 ketone, 1 alcohol, or an acid or an ester. So again, they don't expect you to know the exact answer, but this thing suggests given the data given here. So when I look at T, for example, what I realize for T is above this region I'm highlighting right now is your fingerprint region. I don't care about that. But this highlight that I'm just doing right now, this is your, because of your CO bond in your molecule, because CO double bond shows up at 1700. And then you have this beautiful, lovely broad peak. So the very broad peak from 2500 to 3500 is OH found in CO2H. So which means T is a carboxylic acid. Okay? And you make a 3 carbon carboxylic acid. Capish? Alright. Then U has a thing present and a thing missing. So what's present? First of all, I will ignore fingerprint region. So what's present after the fingerprint region? A distinct bond similar to the same one here. So both T and U have a C double bond O group. Do you see that? Yeah? But what is O missing? O is missing the OH bond. So there's no OH bond. Neither is the OH of an acid, neither the alcohol. So O has basically no OH group. This would be a CH bond, but very deep, very small, you know. Okay? So there's no OH group. So what do I figure about U? I'd say that U could be, let's see, could be a ketone. Let's make a ketone. So let's say a 3 carbon ketone, and then what? I can't put an OH here. So what do is, because there's no OH, I gotta put another O and then H. But the problem with this structure now is that I can't balance the H's. I need 6 H's, now there are only 4 here. So what I realize is that U must be an ester. 3 carbons, so one possibility, and I'm not saying this is the only possibility, but one could have been this. Has a CO bond and no OH group and C3H6O2. And and as long as you can figure out that this is one possibility, that's all they're looking for. Can you figure out by looking at the graph what is possible? So by looking at this question, I realize that U could be this ester while T is a carboxylic acid. All right? And that's the kind of thing that they'll be expecting you to understand. All right? Yeah. Okay. So if the question was, and this missing a word here, but if they said which of these infrareds is that of butanone and which one is that of butanol, butan-1-ol, how could you tell? And this is the last thing I'm doing right now. So if between butanone and butanol, which is butanone and which is butanol? What does butanone have? Butanone has CO double bond. CO double bond is found in the 1700 region. This is the 1700 region. This is the 1700 region. This fellow has a C double bond O. This fellow doesn't have a C double bond O. Right off the bat, it tells me that A is your butanone. So you'll have to, and they'll say, explain how you figure that out. They'll have to say, because there was a band or a trough at 1700 indicating that it contains a C double bond O bond. And what is the graph missing? That's not, and that makes sure that you know it's not an alcohol. Because if it was an alcohol, it would have to have an OH trough at 3500. There is no trough here at 3500. On the other hand, B must be the alcohol because it has By the way, both of them have the CH. This is a CH bond right here. So that's common to both of them. But in B, this is the OH of normal alcohols. Not acids, because acid ke liye it'll be one broad peak. But it's OH of alcohols. And what doesn't have is, it does not have a C double bond O. So that proves that it is not an ketone, but is definitely an alcohol. This proves it's definitely an aldehyde ketone and not an alcohol. So sometimes what the peaks present can be tested, what the peaks present are you can identify, and also identify what is not present by looking at the peaks. All right. So I'm going to wrap off this half here. There's one thing that somebody asked, I'm going to mention that is this, that when in the previous question, this was not the only possibility for U. There could have been another possibility for U also, which is another ester, which is 1 carbon acid and 2 carbon alcohol that made up the ester for U also. But T, because of only 3 carbons, T only had one possibility. But if they had said more carbon atoms in the molecule, then larger molecules, more possible structures acceptable for T and U. Yep. That was the previous question. This one was this. And so I'm going to wrap this class up right here. And I would like you guys to do slides 28 and 29. And yeah, 27, 28, 29. Could you please do those? So slides for this chapter, do slides 27, 28, 29, okay, skill checks, please. All right. Thank you very much. 27, 28, 29. So this is 27. This one I'd like you to do. Then 28. And then 29. And I'll discuss the answer in the next class. All right? Okay.